Hey there. I'm glad you're here. Tonight, let's drift into the quiet power that lies just beneath our feet. We spend all our time on the surface, on solid ground, but deep down, the earth is a place of gentle, slow, incredible change. We're going to talk about volcanoes, not as symbols of chaotic noise, but as the patient, natural vents of our planet's inner workings. They are the quiet, natural consequence of Earth being a living, moving planet. It's a wonderful thought, isn't it? That beneath our quiet homes, there is such profound, simmering energy, managed and controlled by the Earth's own structure. Take a deep, calming breath with me, and let's begin our slow journey down into the warmth. We start our journey by looking at the surface we stand on, the crust of the Earth. If you imagine the Earth as a perfectly round fruit, the crust is the very thin skin on the outside. It's the solid, cool layer that protects us from the intense heat inside. But this skin isn't whole. It's broken up into large, slow-moving puzzle pieces. These pieces are called tectonic plates. Imagine a beautiful, massive, cracked ceramic plate that is floating on a thick, slightly gooey substance. These large pieces are always moving, but at a speed so incredibly slow, perhaps only as fast as your fingernails grow. They move quietly, patiently over millions of years, and this slow movement is the primary reason why we have volcanoes. The Earth's surface is never truly still. Isn't that fascinating? That we live on a constantly shifting surface, yet we feel so settled and secure? Volcanoes most often appear where these large tectonic plates meet. These boundaries are the gentle, weak seams in the Earth's skin. There are three main ways these plates interact, and each one creates an opportunity for a volcano to form. The first way is when two plates slowly, quietly move apart from each other. This often happens beneath the great oceans, at places called mid-ocean ridges. As the plates separate, the pressure on the mantle, the layer beneath the crust, is gently released. This reduction in pressure allows the molten rock inside the Earth, which we call magma, to well up and fill the gap. It's a slow, quiet process of creation, constantly making new ocean floor and quietly building underwater mountain ranges that stretch for thousands of miles. This magma solidifies as it meets the cold seawater, creating new crust. The second way, and perhaps the way that creates the most spectacular volcanoes, is when one plate slowly, patiently dives under another plate. This is called subduction. When an oceanic plate, which is usually thinner and heavier, collides with a continental plate, the heavier oceanic plate sinks back down into the Earth's hot interior. Imagine a long, heavy rug being slowly pulled underneath a fixed piece of furniture. As this cold, wet rock dives downward, it brings water with it. This water, when carried deep enough into the hot mantle, acts like a very quiet, gentle steam cleaner. It lowers the melting point of the mantle rock above it, causing it to quietly begin to melt. This new, less dense magma then slowly rises toward the surface, finding the weakest points in the overriding plate to vent out. This process creates chains of classic, cone-shaped volcanoes, often forming beautiful island arcs in the ocean, like those in Japan or the Aleutians. The third way volcanoes form is the most mysterious and quiet of all. This happens far away from any plate boundary, in the middle of a large plate. These are called hotspots. A hotspot is a fixed, deep source of extreme heat within the mantle, a kind of stable, cosmic blowtorch, gently pushing heat upward. As the tectonic plate drifts over this fixed hotspot, the heat melts the crust above it, forming a volcano. Since the plate continues to move, the first volcano is carried away and becomes extinct, while the hotspot patiently melts a new spot on the plate, forming a brand new volcano. This creates a long, straight line of volcanoes, with the active one always at one end. The most famous example of this is the beautiful chain of islands in Hawaii, which is a perfect, quiet record of the Pacific Plate's slow, gentle movement over tens of millions of years. Isn't that fascinating? That these powerful forces are are so incredibly consistent and slow, tracing the movements of our planet's skin with such precision. It's important to remember that the Earth is simply trying to release its internal heat. Volcanoes are the planet's natural, slow safety valves. They are not random acts of violence, but the expected, orderly consequence of a vast, hot core trying to cool down. The pressure builds, not dramatically, but over years and centuries, and the volcanoes provide the necessary, gentle release. This entire process is fundamental to the story of Earth, slowly recycling old crust and creating new land, quietly shaping the continents and the ocean floors beneath us. Let's imagine the scale of this slow movement, the entire surface of the Earth constantly reconfiguring itself, all driven by the simple need for heat to escape the deep interior. It is a quiet, geological rhythm.
Now let's take a peaceful, imaginative journey straight down from the solid ground we stand on. We are going to explore the source of all volcanic activity, the incredibly hot but mostly solid region called the mantle. This layer makes up the bulk of our planet, extending down for almost 3,000 kilometers. Imagine a massive, dense sphere of very hot rock. You might be surprised to know that the mantle is not a liquid ocean of fire. Most of the rock in the mantle is actually solid, but because of the extreme heat and pressure, it behaves like a very, very thick, incredibly slow-moving plastic or taffy. This slow, quiet movement within the mantle is called convection. Imagine a pot of very thick soup gently simmering on a stove. The hottest, lightest material near the bottom slowly rises to the top, cools down, and then gently sinks back down to be reheated. The mantle does the same thing, but on a scale of millions of years. This slow internal churning is what drives the movement of those tectonic plates we talked about in the last chapter. It's a gentle, patient engine quietly driving the surface changes above. The heat comes from the Earth's core and from the gradual decay of radioactive elements deep within the mantle. This natural, quiet release of heat is what keeps the engine of plate tectonics running. So if the mantle is mostly solid, where does the liquid rock, the magma, actually come from? Magma is formed in specific places where the conditions allow a small percentage of the rock to melt, usually in increments of 3 to 5%. It is not one continuous ocean of liquid. The magma is less dense than the solid rock around it, which causes it to slowly, patiently begin to rise. Think of a hot air balloon. The hot air is lighter and naturally floats upward. Magma does the same thing, gently pushing its way up through cracks and weaknesses in the surrounding solid rock. This slow, upward migration is the beginning of every volcanic eruption. There are 3 primary ways the mantle rock melts to create this magma. The first way, which we touched on before, is decompression melting. This happens when the pressure on the hot rock is released, such as at a mid-ocean ridge where plates are pulling apart. Even though the temperature stays the same, reducing the immense pressure allows the rock's melting point to drop, causing it to quietly begin to melt. Imagine opening a bottle of carbonated soda. Releasing the pressure allows the gas to escape. The rock doesn't cool, but the conditions for melting are suddenly met. The second way is flux melting, which happens at subduction zones. When the oceanic crust sinks and brings water into the hot mantle, the water acts as a flux, lowering the temperature required for the rock to melt. This is similar to adding salt to ice to make it melt faster. This is the process that creates the stickier, gas-rich magma that leads to those tall, steep, and sometimes explosive volcanoes. The third and simplest way is heat transfer, which happens at hot spots. Here, A plume of extra hot rock from deep in the mantle simply rises and transfers its heat to the cooler rock closer to the surface, causing that shallower rock to melt. This magma then rises to form the quiet, gentle shield volcanoes like those in Hawaii. The composition of the magma is a curious thing, and it determines how a volcano will eventually behave. Magma is not just melted rock. It contains dissolved gases, mostly water vapor and carbon dioxide. Think of those dissolved gases like the carbonation in a soda bottle. When the magma is deep and under enormous pressure, those gases stay dissolved quietly in the liquid. But as the magma rises towards the surface, the pressure lessens and the gases begin to expand and bubble out. This gas content is the explosive engine that drives many eruptions, a quiet force deep down that eventually expresses itself on the surface. Imagine watching that happen in the underground, the slow, gentle expansion of invisible gas as it prepares for its journey to the air above. It is the pressure of the Earth's inner heat, slowly, patiently finding its way out.
When we imagine a volcano, we usually picture a towering, perfect, cone-shaped mountain with a plume of smoke at the top. But just like mountains, volcanoes come in many quiet, beautiful shapes, and each shape tells us a story about the type of magma inside it and the style of its eruption. Let's explore the three main shapes, each a unique expression of our planet's inner fire. The first and largest type is the shield volcano. Imagine setting a warrior's shield face down on the ground. It is broad, gently sloping, and immense. These volcanoes are created by magma that is very runny or low viscosity, like warm honey or thin oil. Because the lava is so fluid, it flows easily and quickly for long distances before it cools and hardens. Instead of piling up into a steep cone, it spreads out, layer after layer, creating a wide mountain with gentle, shallow slopes. The most famous examples are the 5 immense volcanoes that make up the Big Island of Hawaii, which are the largest mountains on Earth when measured from their base on the ocean floor. Eruptions from shield volcanoes are typically effusive or flowing. They are relatively quiet, without the dramatic explosions we often associate with volcanoes. The magma can often simply pour out of a central vent or cracks on the sides of the volcano, creating vast, slow-moving rivers of glowing lava. This is the gentle style of eruption, where you can often walk carefully and safely near the flow, watching the surface cool into black rock while the incandescent lava still flows beneath. Here's something curious. Because the magma is so fluid, the dissolved gases can escape very easily, which is the main reason why the pressure never builds up to cause a huge explosion. The quiet degassing keeps the system calm. The second type, and the one that most closely matches the image in our minds, is the stratovolcano, sometimes also called a composite volcano. These are tall, symmetrically steep-sided cones, like Mount Fuji in Japan or Mount St. Helens in the United States. They are built up over many thousands of years by layers of different materials, a quiet history written in rock. Their layers alternate between thick, sticky lava flows and layers of ash, cinders, and broken rock fragments ejected during explosive phases. The name composite simply means they are made of a composite or mix of these different materials. Stratovolcanoes are typically found at subduction zones, where the magma is much stickier or high viscosity, like thick peanut butter. Because this magma is so thick, the gases inside it cannot escape easily. The gases stay trapped, building up immense pressure as the magma rises towards the surface. When the pressure finally overcomes the strength of the surrounding rock, the eruption is often sudden, forceful, and explosive, sending columns of ash high into the atmosphere. This is the more dramatic, though still naturally occurring, style of eruption.
You might be surprised to know that the steep sides are formed precisely because the sticky lava doesn't flow very far before it cools, piling up right near the central vent. The third type is the smallest and simplest, the cinder cone. Imagine a perfectly small, symmetrical mound, often found on the flanks of a larger volcano. These cones rarely grow taller than a few hundred meters. They are built almost entirely from small fragments of frothy, gas-filled lava called cinders or scoria. During an eruption, the magma is thrown a short distance into the air, solidifies quickly as it falls, and lands around the vent, forming a simple, bowl-shaped crater at the top. Cinder cone eruptions are usually short-lived, sometimes lasting only a few weeks or months, and they are often created in a single episode. Let's imagine watching that happen in the sky above, a quick, elegant fountain of lava fragments falling back to Earth to build a perfect, quiet little cone. Each shape is a natural consequence of the magma's viscosity and gas content. Runny magma creates wide, quiet shields. Sticky magma creates tall, often explosive, stratovolcanoes. And frothy magma creates small, simple cinder cones. The Earth has many ways to release its heat, and these three quiet forms are the most common expressions of that deep internal process.
To understand how a volcano works, we must quietly look at its inner workings, the hidden parts, beneath the beautiful mountain we see on the surface. Every volcano has a complex, interconnected plumbing system that stores the magma and guides it on its slow, steady journey from the mantle to the air above. The heart of this system is the magma chamber. The magma chamber is a large underground reservoir of molten rock, usually located a few kilometers beneath the Earth's surface. Imagine a large bulbous balloon or a quiet underground lake of incandescent glowing liquid. This chamber is where the magma rests and collects after its initial, slow rise from the mantle. It is not always a perfect open space. It is often a network of cracks and pockets within the hot, solid rock, where the pressure and heat keep the magma fluid. Here's something curious. The magma doesn't just sit there waiting. This chamber is a busy, dynamic place where important changes occur. While resting in the chamber, the magma undergoes a process called differentiation. As the magma cools slightly, different minerals begin to crystallize out of the liquid at different temperatures. These denser crystals can gently sink to the bottom of the chamber, leaving the remaining liquid magma with a slightly changed chemical composition. For example, a magma that started as a runny basaltic type might slowly evolve into a stickier and acidic type over time, as certain minerals crystallize out. This quiet, chemical evolution is one of the reasons why a single volcano can have different types of eruptions over its long history. It's a slow, subterranean chemistry lab, constantly refining its product. As the magma chamber slowly fills and the magma differentiates, pressure begins to build. Remember those dissolved gases we talked about in Chapter 2? They're beginning to expand, and new magma is continually flowing up from the mantle to replenish the chamber. When the pressure inside the chamber exceeds the strength of the surrounding rock, the magma is forced to find a pathway to the surface. This pathway is called the conduit. The conduit is essentially the volcano's main chimney or pipe, a vertical or near vertical channel that connects the magma chamber to the central vent at the summit. Think of it as a quiet elevator shaft for the magma. This path is often carved out by repeated eruptions over time. Magma moving up the conduit is moving under immense pressure, and as it gets closer to the surface, two critical things happen simultaneously that prepare it for eruption. First, the pressure from the overlying rock steadily decreases. As the pressure lessens, the dissolved volatiles, those water vapor and carbon dioxide gases, begin to come out of solution and form bubbles. This is like shaking a can of soda and then slowly opening it.
The gas bubbles expand rapidly, forcing the liquid magma upward with tremendous energy. This process is called vesiculation, the quiet, invisible engine of eruption. Second, the rising magma cools slightly. In stratovolcanoes, where the magma is already sticky, this slight cooling causes the magma to become even thicker or more viscous. The combination of thick magma and rapidly expanding gas bubbles creates a very dangerous situation. If the magma is too sticky, it can clog the conduit, acting like a cork in a bottle. This blockage causes the pressure to build to extreme, overwhelming levels until the volcano erupts explosively, shattering the cork and sending vast amounts of fragmented rock and ash into the sky. Let's imagine watching that happen in the sky above, a pressure cooker slowly building its energy beneath the quiet mountain. If the magma is runny, like in a shield volcano, the gases escape easily and the magma flows quietly over the rim. If the magma is sticky, the whole system becomes plugged, leading to a much more dramatic yet still natural release of pressure. The entire system is a gentle balance of heat, pressure, and rock strength, a complex piece of natural engineering that dictates the quiet power of the eruption.
Volcanoes express themselves in many ways, but nearly all eruptions fall into one of two primary styles: effusive or explosive. These two styles are completely different in their quiet expression, yet they are both driven by the same fundamental ingredients: magma, heat, and gas. The difference, as we have gently learned, comes down entirely to how easily the gas can escape the molten rock. Let's start with effusive eruptions, which are the calmer, quieter, and more predictable style. These are the classic flows of lava, most often associated with the broad, gentle shield volcanoes like Kilauea in Hawaii. Imagine a thick syrup slowly pouring over the side of a glass, unstoppable but not fast or violent. The magma that causes effusive eruptions is basaltic, which means it has a low silica content, making it very fluid and runny. It is like hot water compared to molasses. Because the basaltic magma is so fluid, the dissolved gases, the water vapor and carbon dioxide, can bubble out and escape very easily as the magma rises up the conduit. Think of it as opening a perfectly still, unshaken bottle of soda. The gas gently fizzes out without any great fuss. As the gases escape, the pressure is constantly and quietly relieved, preventing any massive buildup that would lead to an explosion. This results in the magma reaching the surface and simply flowing out. These lava flows can be immense and destructive to property, but because they move slowly, people can usually evacuate safely. Here's something curious. These flows can cover vast distances, sometimes flowing for tens of miles, gently remaking the landscape as they cool into hard, dark rock. Now let's look at the second, more dramatic style: explosive eruptions. These are the powerful, sometimes catastrophic events that launch clouds of ash and fragmented rock high into the atmosphere, often associated with the steep-sided stratovolcanoes. These eruptions are driven by the exact opposite magma type, andesitic or rhyolithic magma, which has a very high silica content, making it thick and sticky or highly viscous. When this thick, sticky magma rises, it acts like a cement mixer, trapping the expanding gas bubbles inside. The gas tries desperately to escape, but the stiff, viscous magma holds it tightly, allowing the pressure to build and build and build within the magma chamber and conduit. The pressure can reach incredible levels, far exceeding the strength of the surrounding rock. Imagine corking a champagne bottle and then slowly heating it. The pressure becomes enormous. When the breaking point is reached, the effect is sudden and forceful. The sticky magma explodes violently, shattering into billions of tiny pieces of glass and rock,
which we call volcanic ash, and pyroclastic material. This is the process of fragmentation, where the liquid rock is instantly turned into solid particles by the force of the expanding gas. This ash is then blasted miles high into the sky, sometimes reaching the quiet, cold upper layers of the atmosphere, or it flows down the sides of the volcano in devastating, fast-moving currents of superheated gas and rock called pyroclastic flows. You might be surprised to know that there is a quiet spectrum between these two extremes. Some eruptions are fountaining, where lava is thrown high but falls back to form cinder cones. Others are phreatomagmatic, where the magma interacts suddenly with groundwater or surface water, causing a violent steam-driven explosion. But the fundamental lesson is always the same. Gas and viscosity are the quiet, critical determiners of the volcano's demeanor. Runny magma lets the gases escape gently, leading to a flowing eruption. Sticky magma traps the gases relentlessly, leading to a forceful, explosive eruption. Imagine watching that happen in the sky above, a perfect demonstration of pressure and chemistry dictating the Earth's fiery release.
When a volcano finally gives way and erupts, it releases a variety of materials onto the Earth's surface and into the atmosphere. These volcanic products are not just simple rock. They're a complex mix of liquid, solid, and gas, each with its own quiet behavior and unique role in shaping our planet. Let's take a calm look at the three main things that come out of a volcano: lava, ash, and gas. First, let's look at lava. Lava is simply the term for magma that has reached the Earth's surface. Its appearance and movement are entirely dependent on its composition. We can see two primary types of lava flows, both of which are very characteristic of the low-viscosity basaltic magma from shield volcanoes. The first is called pahoehoe, pronounced pahoehoe. Imagine a sheet of warm, thick icing cooling down. Pahoehoe lava flows is smooth, billowy, and sometimes ropey in appearance. It flows relatively slowly, and when it cools, it creates a gentle, fluid surface. The second type of basaltic lava is called aa, pronounced aa. This lava is slightly cooler and thicker than pahoehoe. Because it is thicker, its surface cools quickly and breaks up into sharp, angular, and rough fragments, making it a difficult and noisy type of terrain to walk across when it's hardened. Interestingly, a single lava flow can sometimes start as the smoother pahoehoe and transform into the rougher aa as it travels and cools. Lava flows from the stickier, high-viscosity magma, like the andesitic and rhyolitic types, are often much thicker and move extremely slowly, sometimes only a few feet a day. These sticky flows tend to pile up near the vent, forming blocky, steep-sided mounds called lava domes. Let's imagine watching that happen in the sky above. A slow, gentle, unstoppable push of extremely thick material, barely moving, yet demonstrating immense internal pressure. Next, we look at the solid fragments ejected during explosive eruptions, collectively known as tephra, or more commonly, ash. Volcanic ash is not like the soft, powdery ash from a wood fire. It is actually tiny fragments of glass, minerals, and rock, essentially pulverized magma that has cooled almost instantly in the air. Ash is incredibly abrasive, heavy when wet, and can be transported by the wind for hundreds or even thousands of miles. This quiet, airborne material can pose a serious hazard to aircraft engines and can blanket whole regions, causing roofs to collapse and disrupting daily life. The larger fragments of solid material are given different names based on their size. Lapilli are pea-sized to walnut-sized fragments, and volcanic bombs are streamlined chunks of lava that were ejected while molten and cooled into aerodynamic shapes as they flew through the air. You might be surprised to know that these solid fragments are what slowly and patiently build up the steep sides of the stratovolcanoes.
They are the quiet building blocks of the most famous volcanoes on Earth. Finally, we have the gases. These are perhaps the quietest and most invisible volcanic products, yet they are crucial for driving the eruption and have long-term effects on our atmosphere. The most abundant volcanic gas is water vapor, or steam. The second most common gas is carbon dioxide. Other gases include sulfur dioxide and small amounts of hydrogen sulfide and hydrogen chloride. While water vapor mostly returns to the cycle as rain, sulfur dioxide is a curious gas. Once in the atmosphere, sulfur dioxide reacts with water vapor to form tiny droplets of sulfuric acid, creating a fine haze called aerosols. This haze can linger in the upper atmosphere for months or even years, gently reflecting sunlight back into space. This reflective shield can, in turn, cause a slight, quiet, temporary cooling effect on the entire planet. Isn't that fascinating? That the invisible breath of the Earth can momentarily adjust the global temperature. A quiet, profound example of how connected all Earth systems truly are. The gases are the invisible key to both the eruption's power and its environmental reach.
Volcanoes do not erupt continuously. They have long periods of quiet rest. This brings us to the fascinating concept of the volcanic life cycle, which includes being active, dormant, or extinct. Understanding these quiet phases is crucial for appreciating the long-term, patient history of our planet's fiery vents. An active volcano is one that is currently erupting or has shown signs of unrest, such as earthquake swarms or gas emissions, within recorded human history. These are the mountains we monitor most closely, knowing they are simply in a temporary state of quiet waiting. A dormant volcano, sometimes called a sleeping volcano, is one that has not erupted for a very long time, sometimes hundreds or thousands of years, but still has the potential to become active again because its plumbing system, the magma chamber and conduit, is likely still intact and could be refilled by rising magma. It's a quiet promise that its time might come again. An extinct volcano is one that scientists believe is highly unlikely to ever erupt again. This classification is usually based on careful geological evidence, such as the complete cooling and solidification of the magma chamber, or the movement of the tectonic plate that has carried the volcano far away from its heat source, as is the case in the Hawaiian chain. Determining if a volcano is truly extinct can be difficult, as some volcanoes have rested quietly for hundreds of thousands of years before suddenly waking up. You might be surprised to know that there is no absolute, universal cutoff time for a volcano to be called extinct. It is a classification based on geological confidence and the quiet, long-term history of the region. Now let's explore a spectacular and quiet consequence of massive explosive eruptions, the formation of a caldera. A caldera is a large, cauldron-like depression that forms when a volcano erupts so violently and empties its underlying magma chamber so completely that the structure of the mountain is no longer supported. Imagine a deep, massive balloon filled with air. If you deflate the balloon suddenly, the ground above it will collapse inward due to the sheer force of gravity. This creates a huge circular basin far larger than the original summit crater. The name caldera comes from the Spanish word for cauldron. They are often very beautiful circular basins that later fill with water, forming deep, quiet caldera lakes, such as Crater Lake in Oregon, United States. The formation of a caldera is often the last massive event in a volcanic area's life cycle. Let's imagine watching that happen in the sky above, the entire summit of a mountain slowly, gently collapsing into the void left by the rapidly erupted magma. It is a quiet, profound act of geological self-destruction. The largest and most famous calderas are often associated with what are sometimes called supervolcanoes.
The term supervolcano isn't an official scientific term, but it is used to describe a volcano that has produced an eruption of truly global, colossal scale, measured as a magnitude of 8 on the Volcanic Explosivity Index. The quiet, enormous Yellowstone caldera in the United States is a perfect example of this. The magma chamber beneath Yellowstone is immense, and its quiet, last major eruptions fundamentally changed the atmosphere and climate across the entire globe for years. However, the vast majority of dormant and active volcanoes are much smaller, and most eruptions are minor events. The long periods of dormancy are a gentle reminder that the Earth's processes operate on geological timescales that dwarf our short human lives. A volcano that hasn't erupted in 10,000 years might still be quietly in its sleeping phase. The time it spends resting is far longer than the time it spends active, and during this rest, nature gently takes over, covering the mountain with forests and creating beautiful, fertile landscapes. The Earth is a patient gardener, and the volcanoes are the quiet, temporary breaks in the garden floor.
Water is one of the most powerful and quiet influences on volcanic activity, both as a source of melting in the mantle and as a boundary for the most prolific volcanic regions on Earth. Let's gently explore the connection between volcanoes and the vast blue oceans that cover most of our planet. The most famous volcanic region is called the Ring of Fire. This is not a continuous actual ring of burning mountains. It is a quiet, massive, horseshoe-shaped area that stretches around the basin of the Pacific Ocean. Imagine drawing a gentle, sweeping curve that touches the coasts of South America, North America, stretches across the Aleutian Islands, down to Japan, and continues to the islands of Southeast Asia. This single area contains over 450 volcanoes, which is about 3/4 of the world's active and dormant volcanoes. Here's something curious. The Ring of Fire exists almost entirely because of subduction zones. Along this massive boundary, the heavy, dense oceanic plates of the Pacific, the Nazca, and others are quietly, patiently diving and being consumed beneath the surrounding, lighter continental and oceanic plates. As we learned, this process of subduction introduces water deep into the mantle, causing the rock to melt and form the sticky, gas-rich magma that rises to form the spectacular chain of stratovolcanoes along the continental edges and the island arcs in the ocean. This process is so slow and steady, yet so powerful, that it has defined the entire rim of the world's largest ocean. We must also quietly consider the volcanoes that exist entirely underwater. The largest volcanic system on Earth is not on a continent, but deep beneath the ocean, the Mid-Ocean Ridge System. This vast submerged mountain range circles the globe like the seam on a baseball, stretching for over 40,000 miles. It is the site of the quiet, continuous decompression melting, where tectonic plates are slowly pulling apart. New oceanic crust is constantly and quietly being created along this line. The eruptions here are almost entirely effusive, pouring out runny, basaltic lava onto the ocean floor. The instant the hot lava meets the cold seawater, it cools and hardens into strange, pillow-shaped forms. These are called pillow lavas, and they stack up to form the vast, quiet underwater mountain chain. Most of these eruptions are completely invisible to us, occurring thousands of feet beneath the surface. It is a peaceful, slow, constant process of planetary renewal. Imagine watching that happen in the deep, silent trenches of the ocean, new land being born in the dark, cold water. Water is also responsible for a special energetic type of explosion called a phreatomagmatic eruption. This happens when rising magma encounters a large supply of surface water or groundwater, such as a lake or aquifer. The extreme heat of the magma instantly flashes the water to steam. Steam occupies a much greater volume than liquid water, and this rapid expansion creates a powerful, sudden, steam-driven explosion that shatters the magma into fine ash and blasts it outward. These eruptions are often quieter in terms of the initial magmatic event, but far more energetic due to the steam expansion. You might be surprised to know that water vapor, released by volcanic activity over billions of years, is the original source of most of the water in our planet's oceans and atmosphere. Early Earth was extremely hot and dry. The quiet, persistent outgassing of volatiles from volcanoes, mostly water vapor, slowly, patiently built up the atmosphere, which then cooled enough to condense and fall as rain, filling the ancient basins to form the oceans we know today. Volcanoes are not just destroyers, they are fundamental creators, giving us the very water we drink and the air we breathe. The Earth is a magnificent, self-contained system.
While we often think of volcanoes as destructive, they are actually one of the quiet, essential engines of life on Earth. They are deep, natural furnaces that recycle materials, create the air we breathe, and provide the foundations for the richest ecosystems on the planet. Let's gently explore the deep connection between volcanoes and life. One of the most obvious positive impacts of volcanoes is the creation of incredibly fertile soil. Volcanic rock, or igneous rock, is rich in minerals and nutrients. Over time, lava flows and ash deposits break down through quiet weathering, releasing essential elements like potassium, phosphorus, and calcium back into the ground. These minerals are vital for plant growth, and as a result, the slopes surrounding active volcanoes, even in tropical areas, are often covered in incredibly lush, dense vegetation. Farmers have known this for centuries, and many of the world's most productive agricultural regions, such as those in Italy or Indonesia, are found on volcanic soil. The quiet destruction is always followed by incredible, vibrant renewal. Here's something curious about life and volcanoes. The very first life on Earth may have begun near deep-sea volcanoes. These underwater volcanoes create unique environments called hydrothermal vents. Imagine a giant underwater chimney venting out superheated, mineral-rich water. These vents are usually found near the mid-ocean ridges, where magma is close to the surface. The mineral-rich fluid that comes out of these vents is often black or white, depending on the mineral content, and it creates a thriving, unusual ecosystem. In these deep-sea environments, far from the sun's light, life does not rely on photosynthesis. Instead, it relies on a process called chemosynthesis, where specialized bacteria draw energy from the chemicals in the vent fluids, particularly sulfur compounds. These bacteria form the base of an entire food web, supporting strange, wonderful creatures like giant tube worms and unique species of clams and shrimp. This quiet, self-contained ecosystem, fueled by the Earth's internal heat, is thought by many scientists to be a perfect model for how life might have first emerged on our planet billions of years ago. Volcanoes also play a quiet, critical role in regulating the Earth's long-term climate over geological time. As we discussed, volcanoes release carbon dioxide into the atmosphere. This gas is a powerful greenhouse gas and contributes to warming the planet. However, a cooling Earth is always followed by a geological process that pulls that carbon dioxide back out of the air. This process, called weathering, involves volcanic rock absorbing the carbon dioxide from the atmosphere when it rains, and then the carbon being slowly carried to the oceans. This vast, slow-motion cycle involving volcanic creation and rock absorption is known as the carbon silicate cycle. This cycle acts like a quiet planetary thermostat. If the Earth gets too cold, the weathering process slows down, allowing more volcanic carbon dioxide to build up in the atmosphere, which gently warms the planet. If the Earth gets too warm, weathering speeds up, absorbing more carbon dioxide and cooling the planet down. This entire massive self-regulating process takes hundreds of millions of years, but it is one of the key reasons why the Earth has remained habitable for 4 billion years, unlike our neighbors Mars and Venus. Let's imagine watching that happen in the sky above, the Earth itself breathing in and out, slowly balancing the heat from the atmosphere with the materials from its crust. The volcanoes are simply the vents that keep the process going, ensuring the constant, quiet exchange that sustains life. It is a beautiful, self-correcting system, demonstrating that the Earth is not a passive rock, but a dynamic, living entity that cycles its energy and material for the benefit of all the life that quietly relies on it.
Our quiet journey ends by looking beyond Earth's atmosphere to see how volcanic processes manifest on other worlds in our solar system. You might be surprised to know that Earth is not unique in its ability to produce volcanic activity. The same gentle, powerful forces of internal heat and pressure are at work in other celestial bodies, creating structures that are both familiar and wonderfully strange. The planet that bears the clearest, quietest scars of massive volcanic activity is Mars. While Mars is considered volcanically dead today, its past was marked by colossal eruptions. Home to Olympus Mons, the largest known volcano in the entire solar system. Imagine a shield volcano so immense that its base would cover the entire state of Arizona, and its peak rises over 21 kilometers high, almost 3 times the height of Mount Everest. Its sheer size is a testament to 2 curious things. First, that Mars, unlike Earth, does not have tectonic plates that move. The planet's crust remained stationary over a fixed hotspot for billions of years, allowing the magma to pile up in one spot continuously. Second, Mars has much lower gravity, allowing the mountain to grow to such colossal, quiet heights without collapsing under its own weight. But the most actively volcanic world in our solar system is not a planet at all. It is a moon. Io, one of the 4 large moons orbiting Jupiter, is a quiet geological powerhouse. Io has hundreds of volcanoes, many of which are erupting constantly. The eruptions are not driven by the kind of internal radioactive decay that heats Earth and Mars. Instead, Io is heated by powerful tidal forces. As Io orbits the giant Jupiter, the immense gravitational pull of Jupiter and its other large moons, Europa and Ganymede, constantly squeezes and stretches Io's interior. This constant rhythmic gravitational kneading creates incredible friction and heat, turning the moon's inner layers into a molten mess. The volcanoes on Io erupt with sulfur and sulfur dioxide, giving the moon a striking, beautiful color palette of yellows, whites, and oranges. The eruptions are often massive plumes that shoot hundreds of kilometers into space. It's a fantastic, quiet demonstration of how a non-traditional heat source can still drive the volcanic process. Let's imagine watching that happen in the sky above, a tiny moon constantly spewing colorful material into the darkness of space, all because of the steady, rhythmic pull of its enormous parent planet. Even the small icy moons in the outer solar system have their own unique form of volcanism called cryovolcanism, or ice volcanism. This happens on moons like Enceladus, a moon of Saturn, and Triton, a moon of Neptune.
Here, the material being erupted is not molten rock, but a mix of water, ammonia, and methane, which act as the magma. On Enceladus, massive geysers of water ice and vapor erupt from cracks near its south pole, quiet tiger stripes that vent material into space. This material comes from a vast subsurface ocean kept liquid by those same gentle gravitational tidal forces from Saturn. This cryovolcanism is one of the most exciting discoveries in planetary science because it suggests that these icy moons have liquid water and internal heat, which are two essential ingredients for life. The quiet, gentle plume of water coming from Enceladus is a constant, subtle beacon in the cold, dark void. You might be surprised to know that studying the quiet, different forms of volcanism across the solar system helps us understand Earth better. Each world is a laboratory, showing us how factors like size, gravity, and heat source affect the final expression of geological power. From the immense, quiet, extinct shield of Olympus Mons to the sulfur-spewing powerhouse of Io and the water vapor plumes of Enceladus, volcanism is a universal process, a fundamental way for celestial bodies to release their internal energy. Our home planet's volcanoes are simply one variation in a vast planetary collection. And so our quiet, gentle journey through the fiery heart of the Earth comes to an end. We've seen how volcanoes are not bursts of chaos, but the patient, necessary vents for the Earth's long, slow internal rhythm. They are the quiet evidence that our world is alive, moving, and constantly renewing itself, from the slow drift of the tectonic plates to the invisible escape of gas that shapes our atmosphere. The Earth is a magnificent, self-regulating machine, and the volcano is simply its profound, beautiful way of breathing. The universe is full of mysteries, but for now, let's rest under its quiet, steadfast light. May you find peace, knowing that the ground beneath your feet is part of a slow, majestic, and entirely natural cycle. Rest deeply now under the quiet, steady watch of the world. Good night.